If you want, you can share your
sure.
screen.
Yeah. Can you see the full screen?
Yes, we can see. So when you want, you can start.
Okay. Thank you, Laura. Thank you all for attending. I'm very happy, especially because it's the first time I can present my work I'm carrying out with Cynthia and Gianluigi mainly during this PhD. Can you hear me, right? Just a sign.
Yes, perfectly.
Yes, perfect. Okay. Well, today I will talk about dust evolution in cosmological simulations, but let me briefly sketch out what I'm going to say during the talk. Well, first, it's needed an introduction to dust in galaxies, why it's important, and of course, why you should consider it in theoretical models of galaxy formation and evolution. And then I will move to our one cosmological simulations for better understand our modeling of dust in this context. Then I will go through various results we got recently about dust in galaxies, dust outside galaxies, and this property of grains, but you will see it later on. Just to tell you that much of this talk is based on this very recent paper we just submitted to the journal, is on AstroPH, if you are interested and you want to go into the details of this work. Okay, let me start with a brief introduction to dust, because cosmic dust, yes, is everywhere, is in galaxies, but you have to know what is it and why it's so important before understanding our work. Dust is basically the solid phase of the interstellar medium of galaxies. It's made of very small particles, and I like to say that it's somehow the salt of galaxies, because its abundance, here is very, very low. It's about 1% of the whole interstellar medium mass. But although this few abundance, its role is quite crucial. Let me tell you also a few other stuffs about these dust grains. Of course, you can imagine dust grains are not all equals. There are grains with dimensions ranging from angstrom to microns. Of course, they will follow a certain grain size distribution, as well as the composition of this grain is not fixed. Mainly, the carbon and these atoms, which are called the silicates in our field, are the main atoms which compose dust grains. But there are also other atoms, for example, iron and so on. So you see, there is a strong variety of dimension, composition of these grains, and the effects of this grain is crucial and are a lot. For example, here you see on the right one of the best examples to understand the importance of dust in our galaxies. When you look at a galaxy, this is a typical, let's say, spectral energy distribution for a late-type galaxy. There is a strong contribution of dust, because these grains are able to absorb the ultraviolet radiation coming mainly from AGNs, but also, and most importantly, sometimes from young stars. And absorbing this radiation, they are then able to re-emit it in the infrared region. And we do observe this. Just to tell you that about the 30% of the radiation in our local universe has been dust reprocessed. So it's very important to understand what we are observing. Not only this, but we should also understand the properties of dust, because if you change the properties, for example, the size, the composition of this dust, this spectrum, of course, will change. For example, here you see some spectral features due to some particular species of carbonaceous dust, but I will not go into the details. Just to tell you that when you observe a galaxy, it's better to know which kind of dust it's in it, because otherwise you cannot understand your observation. But another important point is to understand where does this dust come from? And I prepared for you this very simple picture in which I tried to list the most important processes dealing with dust grains. First, these grains are produced by stars, no? Stars produce metals, and a fraction of this metal is condensed into grains. It's very uncertain, this, let's say, condensation efficiency, but we know that they can produce dust, especially supernovae and asymptotic giant branch stars. Once these grains are produced, they will pollute the interstellar medium, of course. And here, there are a lot of processes that may impact on both the mass and the size of these grains. For example, there is dust growth, which occurs in the densest regions of a galaxy, mainly in molecular clouds, in which the gas phase metals are able to accrete dust grains and therefore enhancing the dust mass of the galaxy. But there is also some process which can destroy dust grains. For example, they are destroyed in supernova shocks in the hot phase by thermal sputtering. Not only mass, but also the properties, the geometrical properties of dust may strongly change during the life in the interstellar medium. For example, small grain can coagulate in molecular clouds, large grain may be shattered to form small grains. All in all, the main message is that once dust is produced by stars, it strongly evolves in the interstellar medium, and this is something I will clearly, more or less clearly, show you with our simulations. Finally, important as well, these dust grains may be embodied again in stars, in newly formed stars, as well as metals, with the process that we call abstraction. So this is an inexhaustive picture of all the processes impacting the properties of dust in our galaxies. And once the dust is in the galaxy, not only these processes which are related to the dust grains, but a lot of processes which are related to the galaxy evolution may occur. Here I listed a few of them. For example, one of the most important probably is the formation of molecular hydrogen, which in the low redshift universe or even when there is a small dust abundance, occurs mainly on the surface of these dust grains. And molecular hydrogen is very, very important to allow star formation. These grains may also shield molecular regions from the ultraviolet radiation coming from young stars. They are a fundamental constituent of protoplanetary disks. They promote cooling because when you emit radiation, you cool the gas, of course, and they enhance also the role of radiation pressure. Okay, so all these processes are very important in the broader framework of galaxy evolution. So it's quite natural to account for them. And this is exactly what has been done in the recent years in, let's say, more or less evolved models of galaxy evolution. Although there is no general consensus of all these processes, there have been some more or less interesting attempts in both semi-analytical models and hydrodynamical simulations. These highlighted are two of the works of my group. I was not in the group when they have been done, but in the first one, there is an attempt to model dust evolution in galaxy clusters. In this one, there is an attempt of modeling dust evolution in a Milky Way-like galaxy. Today, what I want to show you is my work, which is basically studying the dust formation and evolution in a cosmological volume. Okay, so considering a broad population of galaxies. I tried to convince you that dust is important, both to understand what you observe, both to understand the effect, the physical effect of galaxy formation. But now I want to show you how we implement dust formation and evolution in the context of cosmological simulations. You know, cosmological simulations are a mess because they aim at modeling processes which occurs in very, very different scales, okay, from the large scale structures of dark matter, which is the field of this very beautiful slide, but also galactic scale processes like winds and so on, but most importantly, what occurs in molecular clouds, okay, so a lot of order of magnitude below the large scale structure by mass and by size, and so it's a very big problem to model all these processes in the same simulation. This is the reason why are often introduced the so-called subgrid recipes. Basically, a subgrid receipt is something you have to assume in order to provide a statistical description of something you cannot resolve. I will be a bit more clear. In cosmological simulations, you have different ingredients that aim at reproducing what you observe in the universe: dark matter, baryons, that is the gas, stars, AGNs. Well, when you have a cosmological volume, you have to, of course, discretize by mass this volume. Each unity of this discretization is a particle. Well, in this particle, there are processes that you cannot resolve. For example, this particle would contain in the real universe a lot of molecular clouds, for example. And for this reason, you need a more or less reasonable prescription to model what you cannot see. Okay, this is why I used before the term in a statistical sense. Well, you can also understand that much of the interesting processes that drive galaxy evolution occurs in these molecular clouds, which are in the interstellar medium. And this is the reason why we adopt our model, which is the MUPPI model, to do this. I will briefly sketch you now how this model more or less work without going into the details, but it's important to understand our implementation of dust in this context. Well, this model is thought to provide prescription for star formation, feedback by stars, by AGN, in the following way. The fundamental unit of this model is this one, which is a multi-phase gas particle. What does it mean, multi-phase? When a gas particle, which is the fundamental unit in the cosmological simulation to trace gas, baryonic matter, becomes dense and cold enough, it can host process of star formation, of course. And this is modeled in the following way, because the hot phase, which is inside this particle, can cool to form a cold phase. Moreover, the cold phase inside always this particle has a fraction, which is the molecular phase, which can bring to newly formed stars. Okay. So this is mainly how this works. Of course, when you produce stars, when you are producing stars, this will have also an impact on the surrounding medium, on the same particle, because they will drive feedback to the interstellar medium, they will heat the hot phase, and so on. So this is the more or less the method used to trace the interstellar medium of simulated galaxies. I will not go into the details of all these equations, which basically follow the processes that I listed you before. Just want to say that this model has been extensively tested on simulations of disk-like galaxies. Here you can find the main references about, and it produces very nice results. Now we are going to test this model also on a cosmological volume. We have some problems I will tell you about in the end of this talk, but for this reason, our main focus will be on the objects we are able to reproduce, which are Milky Way-like, Milky Way mass objects. Okay, so I hope more or less the prescriptions for unresolved interstellar medium physics are clear, now is the moment to see how we put dust in these prescriptions. And of course, we try to emulate what we think happens in the real universe, and we aim at modeling dust using different, let's say, assuming that different kind of dust grains may exist, namely large grains, small grains, silicate grains, and carbonaceous grains. Now, you may ask at this point, but all the dust in the universe is of this kind? Of course, no. There are not only large and small grains. This is a coarse approximation, which is actually really good in their results, and of course is much cheaper from the computational point of view. Again, all the dust is in silicate, all the dust is in carbon. No, of course there are other kind of dust, iron dust, for example, but the main, most of the mass of dust is in these two chemical species, so we are pretty satisfied of this approximation for the moment. But let me show you how this dust model is embodied in the cosmological simulation. As in the real life, the starting point is the stellar particle. The stellar particle aims at tracing stellar populations. So they will enrich the medium from the chemical point of view, of course, by metals, gas phase metals, and a fraction of these metals is condensed into grains. Large grains are mainly produced by stars. Now, inside the gas particle, which is the unit I was telling you before, we assume different processes may act. For example, in the diffuse gas, large grains may shatter to form small grains. These small grains, again, may coagulate in the densest regions of the interstellar medium to form large grains. But there is also a very important process, different very important processes which allow the exchange of mass between the solid phase and the gas phase. For example, these gas phase metals, this one, which are the only one we assume to condense into dust, may accrete mainly and only in our model into small grains, where when there are conditions which are good for accretion, for example, where there is enough dense medium. On the other way, these dust grains may be destroyed by sputtering, by supernova destruction. Of course, all these processes which regulate the relative abundance of large grains, small grains, gas phase metals are modeled through equations that I don't want to show you, but if you are interested, we can discuss about. But the most important point is that these equations are dependent on the physics of the gas particle. For example, the density, the temperature, the molecular fraction in the gas particle. Okay, this is basically, I hope it's more or less clear, basically our implementation of dust inside gas particles in our simulation. And moreover, we assume that dust can cool, that is something that really happens in the universe. Well, I bored you enough with this introduction, but it was needed. Now I can show you a few results. First of all, these nice simulated volumes of gas, stars, dust, different redshift, which have the size of the box of 26 megaparsec, but actually we used a lot of smaller boxes to improve the statistics and also to test our predictions. Let me show you the resolution of the dark matter and the gas particle. This is not important for this work, but just to understand why we need a subgrid receipt, because it's something we cannot resolve. It's exactly what I was telling you a few slides ago. Well, okay, let's go with the results. The first thing I want to show you is the simulated galaxies at redshift 0. We will mainly focus here at redshift 0 and with the particular care to Milky Way yellow mass galaxies for the reasons I told you before. Let me show you the stellar mass function, which is quite good agreement. I mean, it's not a perfect shape, but it's in good agreement with the local observations. The dust mass function is in more or less excellent agreement with our data and also the data available today, and also the scaling relation between dust and stars is in very good agreement. But these stuffs don't tell us very much about all the physics we implemented. So I prefer to move to something more interesting because, as you should have understood, the evolution of dust grains in galaxies in the universe and in our simulation is not only a matter of stellar production. There are also a lot of processes which deserve a lot of attention. And one of these is the process, which are the processes which allow the exchange of mass between gas phase metals and dust grains. This is the reason why I show you here on the left the relation between the ratio between dust and gas and dust to metals as a function of the metallicity of the galaxy. Why I show you this relation? The reason is simple, because since we want to see the relative exchange between dust grains and gas phase metals, this is of course, the first thing you should see. Indeed, it has been widely studied, both theoretical models and observations. Here you see there is a very nice sample of galaxies from the Daspedia project, the point by Davis, which allows us to constrain more or less our model. And you see that our model produces a reasonably good galaxy population in this case. But it's also interesting to see why this relation has this shape. Basically because we can identify galaxies in different regimes. Well, I will show you these ones. For example, at low metallicity, which are typically the low mass galaxies, we are in the so-called condensation regime. Condensation because the dust in these galaxies is mainly produced by stellar population, and it does not evolve toward higher abundances. This instead occurs in the next regime, which is the accretion regime. Here basically happens that you have enough metallicity. That means you have enough abundance of gas phase metals in your interstellar medium. You have hopefully enough cold phase, dense phase, and the accretion process can boost the dust mass toward larger values up to the saturation regime, in which basically gas phase metals are not so able to accrete anymore onto dust grains because they reach the dust to metal ratio reaches high enough values. I want to focus your attention also on the color code of this plot, which is basically the cold gas abundance fraction, because you see galaxies which are more red, which means have more cold gas, are likely to host the accretion process, because I want to recall you that the accretion process occurs in dense molecular clouds and also in our gas particles which have a dense enough fraction. Okay, this is a nice result from our work, but we don't only track the total dust abundance. We also track different kind of dust. And it's also interesting to see how these the different kind of dust as small, large grains behaves in different galaxies. And this is exactly what to show you in these two plots. Here you see on the left the ratio between the small grains abundance and the large grain abundance versus the total metallicity of the galaxy. And here, the ratio between silicate dust and carbonaceous dust. Well, you see there are peculiar trends which maybe are not so easy to understand, but maybe it's easier if I show you these the separation between the various regimes that we identified in the previous slide. For example, in the condensation regime, which is the red region, you have mainly large grains and carbonaceous grains. Then in the accretion regime, the small grain abundance increases, and then it flattens again toward large grains because of the impact of coagulation. In the right plot, instead, you see a very fast increase of the silicate abundance, and this basically tells us that silicates are strongly produced when accretion may play a relevant role. Okay, with accretion, also the silicate abundance is very important. Increases, of course. And just want to tell you that the typical values we obtain for Milky Way hollow mass galaxies, which are the stars, as usual, are in more or less agreement with our Milky Way, of course. But I want to focus also your attention on the fact that not all the galaxies have the same chemical and geometrical properties of grains. This is, of course, clear in light of our model, but it should be also considered when you, for example, perform radiative transfer computations, or for example, when you assume a dust mixture when you perform the said fitting of observed galaxies. So the main message is that not all the galaxies have the same dust, and in light of our model, this is connected to the different regimes of stellar production and accretion of dust grains into the interstellar medium. Maybe it's even more clear, this point, if I show you the evolution of these properties with time and for different classes of galaxies. For example, in these panels, you see the evolution of various properties for the red sample, which is Milky Way hollow mass galaxies, which are basically the most massive one in our simulation, and low mass galaxies, which are the blue one. Let's focus again on the small to large and silicate to carbonaceous ratio. Well, you see that the behavior is quite peculiar, and it may be again related to the accretion in these galaxies. For example, what happened for the small to large ratio? Low mass galaxies will enhance their abundance of small grains because they don't have enough cold gas to admit coagulation, while a sort of equilibrium between coagulation shattering is reached in high mass galaxies, in Milky Way hollow mass galaxies, which have much more cold gas. Here in the top left panel, you see the abundance of molecular hydrogen, which is the one which tracks the abundance of the dense phase. Okay, it's even stranger, much more interesting, if you want, the behavior of the ratio between silicates to carbonaceous. In both these classes of galaxies, in the beginning of the evolution, there is always a domination of silicate grains. What happens then? The carbon increases, the carbonaceous dust increases because of the relevant injection of dust by AGB stars, which you know have much longer time scales of supernova. And now, in the recent times, there is what really distinguish Milky Way hollow mass galaxies and low mass galaxies, which is again the presence of cold gas. Because in large mass galaxies, the red sample accretion is very effective for enhancing the abundance of dust and therefore of silicates, as I showed you in the previous slide. While in low mass galaxies, which have more or less no molecular molecular gas, the accretion will never work, and therefore the dust will be mainly carbonaceous dust. Okay, this is another point of view to tell you what I told you in the previous slide, but it's even more interesting. And if this is not yet so clear, I prepared for you a nice diagram which you can see the life cycle of dust in these different kind of galaxies. The starting point is, of course, stellar production, which produce dust large grains. But then the major role is played by the abundance of cold gas. Okay, if you have enough cold gas, you can do accretion, you can enhance silicate abundance, small grains can coagulate. All these stuffs may not occur into low mass galaxies, which are more likely to have a very low cold gas abundance. Okay. And this is mainly our main physical results about dust properties inside galaxies. And I think for all the reasons I told you above about the size and composition, which is still very unclear of dust grains in galaxies, is very, very, very interesting. This is about dust inside galaxies, but I promised you that I will talk also about dust outside galaxies. Indeed, this is one of the major advantages of using cosmological simulations, in which you have a discretization of the whole volume you are going to simulate, and therefore you can study what happens also outside galaxies. Well, in literature, there are a number of studies. This one, for example, can you see the mouse? Yes, I hope yes. Which tell that there is
Max, I can't see the mouse. I don't know if the other people.
Nice. Vabbè, I hope you understood as well. much of what I said.
I understood more or less.
Yes.
Well, it's difficult to understand why you cannot see the mouse, but the important is that you see the plot here, which show the dust profile around massive galaxies, and this is the results we show here are coming from our and other simulations, but mainly the most important points in this case are the one by Menard, which studied observationally the profile of dust around massive galaxies. And you see up to megaparsec scales, there is a non-negligible abundance of dust grains. Now we want to see if our simulation is able to predict something like this, and actually it does. So we let's say underproduce we have an under prediction of dust on extra-galactic scales. You see more or less the shape and the normalization of the profile is quite similar, and there is also strong uncertainties when you look at other simulations, which are the pink and green lines. But the reason is basically that these results are strongly dependent from what you assume for feedback, for AGM feedback, for galactic winds, and so on. We are not going to tune our model to reproduce this profile, but just want to see if it's work, and more or less modulo all the uncertainties we are pretty satisfied. Moreover, this demonstrates as well that gas and dust dynamics is well coupled. Okay, because for example, you can say you have in your simulation gas particles, stellar particles, but why not introducing dust particles? Well, this has been done by other people, and they also demonstrate that it's not so necessarily. Indeed, you see, when we study something which is basically due to the dynamics of gas, also dust is well reproduced. Okay, this is about dust outside galaxies, but I can bore you again about the properties of these dust outside galaxies. I will be very, very fast. just to show you these two profiles, which are again the profiles of small to large grains and silicate to carbonaceous grains. For example, I can show you that there is always a large grain abundance inside and outside galaxies, while in outside galaxies, this abundance is usually larger because there is much more sputtering, which occurs in the hot phase gas, which is basically outside galaxies, and it easily destroys small grains. You can see also something interesting by looking at the silicate versus over carbonaceous profiles, because you see there is with redshift a non-monotonic trend. For example, at redshift 2, there are a certain number of carbonaceous grains, while at redshift 1, there is still a larger abundance of carbonaceous grains, and then this trend is inverted toward redshift 0, which is the red line, where you have much more silicates, at least inside galaxies. This is because of the reason I told you before, the delay in the production of carbonaceous grains by asymptotic Joy branch stars. And most importantly, you can see that the properties of dust outside galaxies are basically the same of dust inside galaxies if you compare redshift shifted by 0.5 more or less, because dust is essentially produced and reprocessed inside galaxies and then ejected into the intergalactic, circumgalactic, and intergalactic medium. I didn't tell you that these are profiles of the Milky Way hollow mass galaxies and their progenitors. Okay, so we follow in time the evolution of these objects to see what happens to the same objects, of course. So I think I can conclude here for what concerns dust and our I would say more or less nice results, but I want to tell you something more, because as William Shakespeare would say, all that glitters is not gold. And it's also nice to comment on a few problems of our cosmological simulation. One of these is the cosmic star formation rate density. You see here the very famous Madao plot, and you see that our fiducial run, which is the red one, is quite at odds with the observations. Well, we can try to think to a model to improve this. For example, as you see on the right, enhancing the star formation efficiency with dust, because we have the dust modeled in our MUPPI, and so we can do this. And after a bit of tuning parameters, we were able to reproduce quite well the star formation rate density, the blue line. However, we don't want to adopt this model, because you can understand this will change a lot of stuff. So this is postponed to my future work, maybe. Another problem is about the local main sequence. In the local universe, not only in the local universe, in the universe, if you build the plane star formation rate stellar mass, you have a quite tight relation, which is often called the main sequence. And at redshift 0, this main sequence is also reached by another galaxy population, which is the population of quenched galaxies, which is quite below. I don't have the mouse, I cannot show it, but you can understand which is about the main sequence. And you see that our fiducial run, the red one, is not able to reproduce galaxies in this region. So it's still not clear why we have quenched galaxies, probably because of the AGN activity, and for this reason we tried to retune some of the black hole growth and feedback parameters of our simulation, which is the green run in these figures. And you see that we were able to have more or less discrete number of quenched galaxies, as well as a better relation between the black hole mass and the bulge mass. But this is not the focus of our paper. It was just a test we performed, because actually it's one of the first times we try to run our MUPPI model on cosmological volumes. Now, the next steps will be to improve our model also in the context of cosmological volumes, of course, but keeping in mind that we want still to reproduce quite well disk-like galaxies in zoom-in simulations, which is the reason basically why this model was born a lot of years ago. Well, I told you the success, the failures of this work, so I can conclude, I guess. Let me briefly summarize, then you can ask me what do you want. I hope I convinced you dust is an important ingredient of galaxies in both their theoretical and observational understanding. I told you how, more or less, cosmological simulations of galaxy formation work, and mainly how we simulate the interstellar medium of galaxies, and most importantly, how we put dust in this interstellar medium. And the way we put dust is quite good, because we reproduce fairly well the relations involving dust at redshift 0, giving also some important hints that dust is not the same everywhere. This has been already studied, but in this case we show you also the properties, the geometrical, the chemical properties in the simulation. It may be very interesting to see what would be the effect of these properties in radiative transfer computations. And finally, I highlighted you the dust outside galaxies, which is as well important and abundant. The future work will be, I didn't write here, first to fix all the problems we have, then maybe studying in more detail other dust models, for example, a grain size distribution instead of an approximation, a two-size approximation, as well as implementing this the formation of molecular hydrogen on dust grains, which is a work by Cynthia, which is going on in this period, while now, exactly now I'm thinking to reproduce the dust abundance in the universe in local galaxies and high-redshift galaxies with semi-analytical models, which are a bit better, I would say, to better understand the physics which regulate all these processes. Well, I can conclude here. I hope to have been enough clear. Other way, if you want, now I'm here for all the preguntas you want.
Okay, thank you, Max. Before questions, we thank you. Unmute the microphones to clap. Thank you. I'm going to stop the recording now.